Okay, this is chapter 5 that deals with gases and the kinetic molecular theory of gases. And let's get started right away with a bit of an introduction to gases. And gases have been known to exist for a long time, even since ancient times, way back when the ancient Greeks considered gases to be one of the four fundamental elements of nature. Keep in mind, this was more of a philosophy than a science, and I am not an expert in philosophy. But it wasn't until the 18th century that the chemists Lavoisier, Cavendish, and Priestley determined that the air that we breathe, is mostly made up of nitrogen and oxygen. In fact, it's mostly nitrogen. There's a lot of nitrogen in the air and only a little bit of oxygen, with a trace of other components, including argon, carbon dioxide, and water vapor. And so, again, in the 17th century, these chemists or scientists were able to determine, the identity of some different gases that are found in the air that we breathe. And if you look at our modern periodic table, you can see it's a minuscule portion of the periodic table that are elements that exist as gases at 25 degrees Celsius, which is essentially room temperature, and 1 atmosphere, which is atmospheric pressure. And those are all of the elements that are highlighted in yellow. You have hydrogen, and then you have the noble gases, of course, nitrogen, oxygen, chlorine. Right? So there's not very much of the periodic table where we see elements that exist as gases in their natural state. In fact, where are you going to find fluorine, just fluorine gas in, somewhere on planet Earth? I mean, you're not going to find just fluorine gas hanging around. It can be synthesized. Fluorine gas is a really reactive gas. But anyhow, most elements you see are metals. Okay, so the vast majority of elements are metals, very few gases. Now, what about compounds that are gases? This next slide summarizes substances that are found as gases at 1 atmosphere pressure and at 25 degrees Celsius. Oops, there we go. And again, here are the elements, the noble gases. And then we also have ozone thrown in there as well. Ozone is an allotrope of oxygen. Molecular oxygen is O2, and then of course ozone is O3. And we discussed that when we talked about heats of formation of substances in the last chapter. And as far as compounds go, well, gases are molecules that like to be free. They're kind of the hippies of the molecular world. They want to be free, and in order for them to be freely hanging in the air, they have to be small, right? They have to be small compounds, and so that's why we don't find many compounds that exist as gases at room temperature and atmospheric pressure. But you should be aware of all of these gases, okay? If you see, nitric oxide or nitrous oxide, you should be aware that these are gases. In fact, I teach a class, another chemistry class, where we had a question on an exam, I don't know, maybe a week ago or something, and one of the questions had a variety of compounds that you see here, and then it had A, B, C, D, E, and it said, which one of these compounds is not a gas? And one of them was calcium chloride, right? And right away, you would see, well, calcium chloride is the answer, because calcium chloride is an ionic compound. It's made of a metal and a non-metal, and ionic compounds generally have very high melting points, and so they are definitely not going to exist as gases at room temperature. Anyhow, kind of an interesting thing about some of these gases, I don't know if you've ever had the chance to inhale helium. I mean, don't go out and buy a balloon right away, but if you've ever inhaled helium, since helium is molar mass is lighter than the molar mass or the average molar mass of air, the average molar mass of air is around 30 grams per mole, and helium is around 4 grams per mole. And so sound waves are going to travel faster through helium. And so if you inhale helium and then you start speaking, it kind of sounds like, you're one of Alvin or the Chipmunks, Whereas if you Google it or go on YouTube, you can probably find all kinds of videos of people inhaling sulfur hexafluoride, which is a heavier molar mass than that of air or helium. And so when you breathe that in, it's heavier. Sorry, the medium has a higher molar mass, and so the sound waves travel slower, and so you kind of sound like, I don't know who, Darth Vader maybe, I guess. Anyhow, you have a deep voice. But anyhow, something kind of fun or funny for you to Google if you want to take a look at that. What are some of the physical characteristics of gases? Well, we've talked about physical properties of solids, liquids, and gases way back at the beginning of this class. So you probably are already fully aware that gases assume the volume and the shape of their containers. They are the most compressible of all the states of matter. It's, solids are virtually incompressible. Liquids are difficult to compress, but gases are very compressible. In fact, we discussed that even before we began the lecture today. Gases will mix evenly and completely when confined to the same container. So if we mix two or more gases, they're going to form a homogeneous mixture. And gases have much lower densities than those of liquids or solids. In fact, when we look at the densities of liquids and solids, normally those are reported in grams per milliliter or grams per centimeter cubed. Those are the common units that we like to use in chemistry class. Whereas for gases, we use units grams per liter, right? Because there's going to be so little gas in a gram per milliliter that the densities are so low that you have to keep track of all these different zeros, okay? So, so you're basically dividing by a volume that's 1,000 times larger. And that's because gases take up much more space than liquids or solids do. This picture here shows a volumetric flask. And I don't remember exactly what gas is in there. I would guess that it's probably something like bromine. Since it's red, it might be some bromine gas in there. Anyhow, regardless of what the identity of the gas is, the point is this, is that you see how the gas, completely fills the entire container, right? It takes up the volume and it takes up the shape, or it takes on the shape of that volumetric flask. Kind of interesting. Now, in order for us to be able to study gases, we have to have variables, right? In order for us to, to use science in general, we need variables to describe the state of a system. And so the variables that we're going to use to describe the state of a gas are volume, and we use the symbol V for volume. And volume is usually measured in liters. We're also going to use amount, and the symbol that we use for the amount when we use moles is N. So I'll say N is equal to the number of moles, like that. We're also going to use temperature, and the units that we'll use for temperature are Kelvin, and I'll explain why we use Kelvin. And then finally, we're going to use P as our variable for pressure, and we're going to use several units for pressure that you're going to see throughout this chapter and in the textbook. So let's talk about pressure for a second and talk about all the different units of pressure that you're going to be exposed to in this class. Pressure is defined as the amount of force per unit area. Now, if you look at the wall of a tire on your car, you probably see that it says, PSI. So PSI, which is shown, and PSI stands for pounds per square inch. Now, if you think about that, pounds, again, this is just for a PSI, but pressure would be equal to pounds per inch squared, or square inch. Well, if you think about that, that means that when you have a square inch, okay, that means there's a certain amount of force acting on that square inch, and they measure that force in pounds. So it makes sense that pressure is defined as force per unit area. Now, in terms of the pressure that we feel on us while we live here on planet Earth, that pressure that we're all experiencing right now, we call that atmospheric pressure. Now, we don't feel atmospheric pressure. You don't feel anything pushing down on your head right now. And that's because we are under atmospheric pressure at all times. Now, the way that atmospheric pressure was measured is using a very clever experiment that was performed by a scientist by the name of Evangelista Torricelli, okay, who was a good Italian scientist back in the day. And what he did, obviously in Italy, is he took a column of mercury, so basically a very thin tube that he had filled up with mercury right to the brim, okay? And then he did this experiment in Italy, and you probably are aware that most of Italy is surrounded by the ocean. So most of Italy, or a lot of Italy, is at sea level. And he did this experiment at sea level. I always like to imagine him as, at maybe a beach party or something doing this experiment. So he's right at sea level, right? A real swinging cat, this guy, right? So he takes this column of mercury and he has it again filled up right to the brim, and he inverts that column of mercury into a dish of mercury. Okay, he says dish filled with mercury. And what happens is that there's a force of gravity that's going to act on that mercury and start pulling it down. But there's also the force, there's the force of the atmosphere acting on the mercury in the dish that's pushing it back up. Okay, and so the mercury obviously didn't drop all the way down; it dropped a little bit of the way down. And he measured the height of the column of mercury, right? The distance from the top of the liquid that's in the dish to the top of the height of the column. And he measured that as being 76 centimeters. And 76 centimeters, we know that in 1 centimeter, there are 10 millimeters. And so that is equal to 760 millimeters. And we say that atmospheric pressure, or the pressure at the seaside, okay, if you're in California or Nova Scotia or wherever, that 760 millimeters of mercury is equal to what we call 1 atmosphere, or 1 ATM. Now, this is one of the funniest unit conversions that you're ever going to see in any science class, is that the millimeter of mercury is also sometimes called the torr. And you can see that 760 millimeters of mercury is equal to 760 torr. So the unit millimeter of mercury and torr are identical. Okay, and you're like, well, why would you have two? I don't know. I didn't make it up. Just the way it is. Okay. Now you might be wondering about, other units of pressure, like PSI. Well, 1 atmosphere of pressure is equal to 14.7 psi. And then there's another unit of pressure, which is based off of the number of newtons per meter squared, and we call that the Pascal. So 1 atmosphere is equal to 101,325 pascals, or 101.3 kilopascals. Because, yes, you can imagine, in 1 kilopascal, there's 1,000 pascals. Anyhow, there we go. Let's see here. I'm just trying to think different things I want to tell you about. Any questions about this slide? Sometimes Mr. Deon has an inner monologue that he lets out, just thinking out loud, things I want to tell you. But I think I've covered everything I want to talk about here. Has anybody heard of this experiment before, Torricelli's experiment, where they take the column of mercury? Because I think the actual column of mercury is actually much narrower than what it looks like here. Here it looks like it's looks like it's the size of a test tube, but I think it's very thin, a very thin glass tube. All right, well, where is the atmospheric pressure coming from? If you have a pot of water, let me ask you guys a question. You got time. If you have a pot of water, if you ask most people who know anything about science at all, and you say, what's the boiling point of water? What's the temperature where I can take water in the liquid phase and convert it into water vapor, water in the gaseous phase? And most people will say the boiling point of water is 100 degrees Celsius. But that's at 1 atmosphere. Okay? Here in Colorado Springs, we are below 1 atmosphere of pressure, right? We have low air pressure here because we're at higher altitude. Could anybody tell me, in Colorado Springs, would water boil at 100 degrees Celsius, or lower or higher than 100 degrees Celsius? Would the water boil lower or higher? Yeah, the answer is that the water is going to boil at a lower temperature, right? So in Colorado Springs, so this is at 1 atmosphere, or 760 millimeters of mercury. And I wrote down here in my notes, in Colorado Springs, the atmospheric pressure is around 616 millimeters of mercury. Now, I have a barometer on my phone, and I checked that probably last semester or something. But let's just say it's significantly lower than atmospheric pressure. And so the boiling point of H2O is going to be less than 100 degrees Celsius. Now, let's see if we can rationalize why that is. If you are at, the seaside, okay, and you have your pot of water, let's say that the bottom of this column of air is at the seaside, okay, or, at a lake that's at sea level. Well, you have all the pressure of this column of air pushing down on the molecules that are in the liquid phase, right? So as they're trying to escape into the, I don't know why I keep trying to write mercury. Anyhow, as they keep trying to escape into the gas phase, you have atmospheric pressure pushing those water molecules down, saying, get back, I'm stamping the floor, get back into that pot of water, you water molecules, okay? Now, if you're in Colorado Springs, so I'll draw Colorado Springs. Here it is. This is Pikes Peak. Okay, here's your pot of water. Okay, so you and I are boiling some water on top of Colorado Springs, or on top of Pikes Peak. Crazy. Anyhow, now I'm going to try to draw the column of air the best I can. Okay, so the column, is there a column of air pushing down those water molecules that we're trying to boil on top of Pikes Peak? Yes, but are they as hot? Is there as much? No, right? Because you just don't have all that extra volume. And so pressure pushing those water molecules back into the liquid phase. And so it's easier for the molecules to escape into the gaseous phase, H2O gas. Give me a thumbs up if that makes some sense to you. All right. So, I mean, you can go on Mount Everest, where I think the pressure is something like 500 millimeters of mercury. In the second college that I worked for in Canada, they had a question on one of their exams, which was based off of the atmospheric pressure. It's not a problem we would solve in this class. I think it was in Gen Chem 2 or something, but it said basically, going off of the atmospheric pressure on top of Mount Everest, how long would it take to boil an egg? Okay, because the water boils at something like 70 degrees Celsius or something on the top of Mount Everest. Okay, another example would be what else? I'm trying to think here. When I first moved to Colorado Springs, has anybody in the class lived by the ocean, or lived, maybe in New Jersey or New York or California or something, Florida, where you're next to the ocean? If you live near the ocean and you're used to cooking near the ocean, you'll notice that pasta cooks much faster than it does in Colorado Springs, right? And the reason why is because the water near the ocean boils at 100 degrees Celsius. And so when the water's boiling, it's at a higher temperature than here in Colorado Springs. Here, the water boils at something like 94, 93 and something degrees Celsius. And so it always takes longer to cook the pasta. Anyhow, really get an Italian thing going on today. All right. A long time ago, a number of years ago, I went to Cuba. Since I'm Canadian, I'm allowed to go to Cuba. And I went to Cuba to recover from a surgery, which I know as an American, you're probably thinking, what? Yeah, anyhow, I was really sick. And I went to Cuba to recover from this surgery. And while I was there, I met an Italian guy. And we'd go, to the beach once in a while. And we remember standing in the water with him and being really sick. And I remember him saying to me, he said, "Hey, Dan, the water, she's warm enough to cook the pasta." Anyway, good times in Cuba. All right, so how do you go about measuring gas pressure? Well, a barometer is used for measuring atmospheric pressure. So if you've ever watched the news, they'll talk about barometric pressure, but a manometer is used for measuring the pressure of a gas. You can kind of divide this slide in two, really, because we got two kind of scenarios, or two types of manometers, I should say. There's actually three scenarios here. We can have what's called a closed-end manometer. And on a closed-end manometer, you can see it kind of clearly here. We have an evacuated flask, and then we have some mercury in there where the levels are equal. And then we have this end closed. Okay, this end is tight, and we have a vacuum here. So that means there's no pressure in there whatsoever. And then if we introduce a gas into the flask, it's going to push this mercury, it's going to push it down, right, in that direction. And so when that happens, the pressure of the gas can be measured by looking at the change in the height of the column of mercury. So that delta H, whatever that is in millimeters of mercury, that's going to be equal to the pressure of our gas. Now that's with a close-end manometer. I don't call it a manometer because I don't hear anybody call it a barometer, so it's a barometer, so it's a manometer, right? Now, over here on the other side, we've got two two scenarios with what's called an open-end manometer. And of course, if it's open, what does that mean? It's open to the pressure of the atmosphere. So if you have the pressure of the atmosphere acting on your gas, okay, well, that means that before you introduce a gas into the chamber here, that means that the height of the mercury here is going to be lower here to begin with, okay, because, and that's, well, let me make it simpler, okay? You have atmospheric pressure acting on the open end of the manometer. If you introduce a gas into the bulb, okay, it's going to start pushing on the mercury, right? But if the height, if the height of the mercury is higher on the side where the gas is compared to the side where the atmospheric pressure is, that tells you that the pressure of the gas is less than atmospheric pressure, right? So in order for you to calculate the pressure of the gas, you have to take the height of the column of mercury and subtract that from atmospheric pressure. The opposite is true if the height of the column of mercury, if it pushes the mercury higher on the side of where the atmospheric pressure is. In that case, the pressure of the gas is greater than atmospheric pressure. And so in order to measure the pressure of the gas, you would tack on the change in the height of the column of mercury to the atmospheric pressure. So these are really three scenarios that you need to know how to calculate the pressure of a gas, okay? If it's a closed-end manometer, it's really simple, okay? Because the pressure of the gas, P gas, is going to be equal to delta H, okay? Which is going to be measured in millimeters of mercury. If the pressure of the gas is less than atmospheric pressure, then you're going to subtract delta H from atmospheric pressure. And if the pressure of the gas is greater than atmospheric pressure, then you add, okay? It makes sense, right? If you're ending up with pressure of the gas being lower, well, then you're going to subtract. And if the pressure of the gas is higher, well, then it makes sense. You're going to have to add something to it, right? Let's look at a scenario here, okay? And this is where we're really going to start getting into gas laws, okay? We're just talking about how to measure gas pressures right now. But how would you study the relationship between pressure and volume of a gas? And even before I started recording this lecture today, I had kind of an interesting discussion with my students who are online. And I said, you know, if you were to take a certain volume of a gas and you were to put it under a higher pressure, what would happen? And, you know, all the students said, well, the volume of the gas is going to decrease. And that's exactly what you see here. Just a simple apparatus that shows we have volume of gas here. That volume is, you know, 50 milliliters. And you can see that we have a pressure, which is atmospheric pressure. I'm going to call that P1 and V1. So 760 millimeters of mercury, like that. What happens when you double that pressure? Look at this. When you increase the pressure, now 760, we take 760 in your calculator, and you can probably do this in your head, and multiply by 2, you get 1520. So if we double the pressure, we increase it to 1520 millimeters of mercury, what happens to the volume? The volume drops, but by how much? Right? The volume drops from 50 milliliters to 25 milliliters. So as pressure increased 2 times, volume dropped by 1/2, right? By a half. This is interesting. And we can actually make a plot of this, okay? If we do this scenario for a bunch of different pressures, we can make a graph of pressure versus volume. Now, before we move on, I want to point out something very important here. Is that, do you remember the variables that I talked about, I don't know, maybe 4 or 5 slides ago or something? The variables that we looked at, let me change the color of my pen here. The variables that I said we were going to look at when we were going to study a gas were volume, temperature, pressure, and number of moles. Now notice that in this experiment, this very simple experiment, that we're looking at volume and pressure. That tells me that if I'm only examining those 2 variables, that means that T, in this experiment, temperature and number of moles are constant. Okay? I am not messing around with those whatsoever. If I wanted to start messing around with those, that's something else. Okay, that's a different study. Okay, but right now we're just looking at the relationship between pressure and volume. And what I was getting at was I can make a plot of the volume of gas at different pressures. And look what happens when you make that plot of pressure versus volume. You get this non-linear curve that's shown here on the left. Now let's look at, two different pressures in two different, or see what the volumes are at two different pressures. So if I, look at this point right here on the curve, okay, that's at a pressure of 0.6 atmospheres, and the volume of the gas is 2 liters. Now, as we said before, if we decrease the pressure, right, as the pressure drops, what's going to happen to the volume? The volume is going to increase. So when I look at this data point, where I have a pressure of 0.3, the pressure dropped by a half, what happens to the volume? It increases twofold, double. Now, what's interesting about these two data points, if you take 0.6, okay, and I'm going to leave the units out, but if you take 0.6 and you multiply it by 2, what do you get? You get 1.2. Look at this data point here. If you take 0.3 and you multiply it by 4, what do you get? 1.2. So that tells me that if I multiply pressure by volume, and that the same thing will apply at these two data points or any data point anywhere along this curve, that the product of pressure and volume is always going to be equal to a constant K. Written another way, I can say that pressure is equal to K divided by volume. Now, I can also rewrite that formula another way. Since K is a constant, I can use this, by taking initial and final pressures and volumes. And I can say that the initial pressure times the initial pressure times the initial volume is equal to the final pressure times the final volume. What does that tell us? Based off of algebra, as long as we have 1, 2, 3 of those variables, and I mean any 3 of those variables, we can always solve for the fourth. Okay? And again, as I told you on the last slide, remember that we're just messing around with pressure and volume. That means that we're at constant temperature and at constant number of moles. Now, this plot that's shown on the left shows this inverse relationship, but it's a non-linear relationship. If we make a plot of pressure versus 1 over volume, we get a linear curve. Okay, so again, when we look at this relationship, PI or P1 times V1 or whatever, however you want to think of it, but we'll do it the way, or I'll read it the way it's written here. PI times VI is equal to PF times VF. This law has a name, okay? And this law is called Boyles Law. Now, for some students, a picture is worth 1,000 words, okay? I'm kind of like that from time to time. So let's look at another representation of Boyles Law. Here we have constant temperature and a constant number of moles of the gas. How do I know it's a constant number of moles? How do I know it's a constant temperature? They told me. How do I know it's a constant number of moles? If you count up all the red spheres, and I'm not doing that, but if you count them all in all 3 vessels, it's the same number each time, okay? Anyhow, look what happens when we increase the pressure. Here's our pressure gauge, okay? We see that we have a certain volume here, and as we increase the pressure, right, we're cranking up the pressure, going from here to here. What happens to the volume? Volume goes down, okay? What happens if we decrease the pressure? Volume goes up, right? That makes sense, right? Because we said that pressure was proportional to the inverse of the volume, right? As P goes up, P is going to go down. As P goes down, V is going to go up, all right? Give me a thumbs up if you just follow me just on that concept, just on that concept so far. Cha-cha-cha-cha-cha. Where are my students? All right, thanks, you guys. Good. Glad you follow with me on that. I think I put too many problems in here. I don't know. Anyhow, let's try a problem that involves Boyles Law. I used to tell my nursing students that it was named after Susan Boyle, the woman who won Britain's Got Talent or whatever. Anyhow, where am I? Where are my students? Sorry. There we go. Boyles Law, we got a 3.5 liter sample of a gas at 1 atmosphere, and it is expanded at constant temperature until the pressure is 0.1 atmospheres. What's the volume of the gas? Look, we're given our initial volume, Okay, we're starting at a volume of 3.5. And our initial pressure is 1.0 atmospheres. They're asking us, what's the final volume? I'm going to call it V2 instead of VF. What is that when we are at a pressure of 0.10 atmospheres? Look, my first question to you is this. I got one question before I start talking to him. Is the volume of the gas going to be greater or smaller? What do you think than 3.5 liters? Will it be more than 3.5 liters? Will it be less? Will it be the same? What's your knee-jerk reaction? What do you think? Just, yeah. I see that Ashlyn wrote more. I think she's on the right track, right? How did she know that so quickly? Well, the pressure is dropping, right? We're going from a high pressure to a low pressure. So as P, right, if P is going down, right, what's going to happen to V? It's going to go up. So our final answer for our V2 should be higher than 3.5 liters. Let's do some algebra here. P1 is equal to V1. Sorry, P1 times V1 is equal to P2 times V2. Okay. We're solving for V2. You should be able to rearrange this formula very quickly. V2 is equal to P1 times V1 divided by P2. We'll plug in some numbers. Our initial pressure is 1.0 atmospheres. Our initial volume is 3.5 liters. And our final pressure is 0.10 atmospheres. You can see that atmospheres cancel. And we're left over with the units of volume with our liters. And we get that our V2 is equal to 35 liters. Does that make sense? Absolutely. Because P decreased by 10. Therefore, V increased 10 times. Right? There we go. Before we move on, I just want to notice some important wording here. Notice that they tell you that you're at constant T. So T is constant. And we know that N is constant because it tells us you have a sample of a gas. It doesn't say anything about introducing more gas or taking gas away. So based off of that, we can assume that the number of moles or the amount of the gas remains constant. So there you have it, my friends. Boyles Law. The names are important. You do have to know the name Boyles Law. You do have to be able to come up with P1, V1 is equal to P2, V2. Okay? If I see you on the street in 5-6 years, you know, first thing I'll say is, hey, do you remember Boyles Law? I'll say, absolutely, I do. I'm going to skip this problem here. We'll come back to this one if we have time. I want to move on and talk about another law, which, again, is another experiment that we discussed this morning. And my students had some really good insight on a question I asked. I said, what if you had a gas, you know, at some temperature, and you increase the temperature? You just cranked up the heat on that gas. What's going to happen? And all my students said, hey, the volume of the gas is going to expand. And this is a really simple experiment. Capillary tubing, if you have never seen a capillary tubes are actually very thin. This looks like it's a test tube, right? It looks huge. But capillary tubes are, wow, they're really small. They're only a couple of millimeters in diameter. So if you take a gas and you put mercury on top of that gas and you have it at a certain temperature and you increase the temperature, right? You go from a low to high temperature. So as the temperature increases, what happens to the volume? The volume is going to increase. Okay? So that means that temperature and volume are directly proportional. So if we plot a graph of volume versus temperature, right? Like this, if we have volume versus temperature, we're going to get a straight line like this. Okay? Notice again that the four variables that we mentioned earlier on in the class were temperature, pressure, number of moles, and volume. I don't have them, you know, memorized in any specific order, but what are we dealing with here? We're talking about temperature and volume. It tells us, right? It tells us right here that pressure and number of moles are constant. Okay? We're not talking about pressure. We're not talking about number of moles. We're going to get to problems where we look at more than two variables. Yeah, absolutely we will. But remember, when we're talking about just volume and temperature, we're making an assumption that that number of moles and pressure are remaining constant. Okay, I'm thinking of too many things here at once. Let's look at this really interesting slide. A lot of information on this slide. In the blue box here, or the blue graph, rather, you see a plot of volume versus temperature. And you see the curves for, a plot of volume versus temperature at 4 different pressures. So maybe one's atmospheric pressure, maybe one's in, Colorado Springs, maybe one's, below sea level. No, I doubt it. Maybe one of them's on top of Mount Everest. I don't know. But you have all these different pressures. And no matter what the pressure, okay, if you're at a constant pressure and number of moles, you can see that you get a linear plot for volume versus temperature. We just decided that volume and temperature were directly proportional to each other. And so if you analyze any of these curves, much the way that we did in the last, or on the last with Boyles Law, you'll see that if you take volume and divide it by temperature, you'll always end up with K, a constant, okay? Or you can rewrite that as it is here. Volume is equal to the constant K times T. Now you can rewrite that formula like this, okay? If you analyze 2 points on the graph, you can say that VI over TI, or V1 over T1, is equal to V final over T final, or V2 over T2, either way. But when you want to use this formula, and both the formulas, the way they're written here, the temperature has to, and I don't like to talk too loudly, I know a lot of people think I have a loud voice, but the temperature has to be in Kelvin. I remember one time, Dr. Diaz, shared his office with me, and I remember him explaining that to a student one time. He was talking so loud, it was hurting my ears. He said, the temperature must be in Kelvin, okay? And the reason why is because if you were to use the temperature scale in degrees Celsius instead of Kelvin, well, then you start putting in negative numbers, right? Once you get below 0 degrees Celsius, and then you get some serious problems, okay? When you're putting in negative numbers, because then the formula won't work. Now, if you're wondering about the Kelvin scale, let's discuss that. And you probably noticed that you're probably thinking like, hey, come on, man, look at all these curves. They all kind of get dashed down here. What's all that about? Well, let's think about a couple of things here. Okay, first of all, if you look at the plot of volume versus temperature, no matter what the pressure is, if you notice, all the slopes of all the lines, they all converge at the same point, okay? And they actually converge at a point that can't be reached, because if you drop the temperature low enough, if you drop it down to negative 273.15 degrees Celsius, what's your volume, okay? You hear me kind of giggling under my breath. What would the volume be at this point? The volume would be 0. Well, can you have no volume? And if you're thinking, well, come on, Mr. Deon, you said, that with an ideal gas, and I don't know if I said this to you guys or not, but I teach too many classes where I talk about gases maybe, but with an ideal gas, we assume that the gas particles have mass, but we assume they have no volume, okay? We negate the volume. Well, there's a couple of things I could say about this, okay? First of all, you see that they all converge at the same point, okay? And that point is where they have a volume of 0, and that is negative 273.15 degrees Celsius. Now, what's the definition of matter? I'm really thinking about a lot of things here. What's the definition of matter? If you go right back to, I think, the first day we met back in August, we talked about matter. Matter has mass and starts with S, ends with space. That's right, space, okay? So if it takes up space, how in the heck would you get to a volume of 0? Well, I bet you there's somebody out there who's listening to me who already knows the answer. And the answer is that this temperature cannot be attained, right? You can't attain what we call absolute 0. So negative 273.15 degrees Celsius, we call that absolute 0. So if you calculate that temperature in Kelvin, and the formula for the conversion between degrees Celsius and Kelvin is shown right here. If you plug in negative 273.15 into this equation, what do you get? You get that the temperature at this point is absolute 0, and that the temperature in Kelvin would be equal to 0 Kelvin, okay? Unattainable, cannot be attained, okay? Because no matter how much you want to, no matter how much you cool them, matter is always going to have some kind of volume. Even an electron, right? If you cool an electron down to, really low temperature, it's still going to take up some space, okay? So this law is called Charles' Law, this law that deals with volume and temperature. The law that deals with pressure and temperature, that is called Gay-Lussac's law, and I'm going to talk about that more in a second. But before we do that, I want to show you a picture, an illustration of Charles' law. Okay, I asked you before the lecture started, I said, what's going to happen if you heat up a gas? And all my students said, oh, it's going to expand. Well, here's a cool experiment that you can do where you actually cool a gas. If you take a party balloon and you just blow it up with, the gas from your lungs, and you take that party balloon, and you pour liquid nitrogen on top of it, look what you can do. This, I was going to insult the person and call them a hobo, but I don't know who it is. That's not very nice. But anyway, you can take all these balloons, and if you pour liquid nitrogen on them, so this is nitrogen in the liquid phase, okay? It's at 77 Kelvin, so it's very, very cold. The air from your lungs is at what, 37 degrees Celsius maybe, okay? So what's going to happen is as the temperature drops, the volume is going to drop, because we know that volume and temperature are proportional to one another, right? We just wrote Charles' law. Charles' law is being V1 over T1 is equal to V2 over T2. Okay, so when you pour that cold liquid nitrogen, you can see the volume of the gas goes down, and I'm not even reading it here. I need a new prescription, but the volume of the air in the balloons as predicted by Charles' law decreases. All the balloons can fit into the beaker. Kind of cool. And then this is the really fun part, is when you take them out, right? You yank them out and they start to fill up, or they start to, I shouldn't say fill up, they start to expand as they get warmer. Give me a thumbs up if you follow me just on the idea, the basis behind Charles' law. I think, this makes some sense to me. I can dig it. Can get me some Charles' law. Yeah, okay. Now, one of the most difficult things about these laws, I find, because, I've taught this class enough to know that I find my students usually find Charles' law, Boyles' law very intuitive. What's the hardest thing? Memorizing the name, okay? So Charles' law deals with volume and temperature. Next, I'll show you Gay-Lussac's law. So, Gay-Lussac's law is shown sort of in the bottom here. Anyhow, on the top, we have the representation of Charles' law. So Charles' law is that V1 over T1 is equal to V2 over T2. If you look at what's happening here, it's kind of funny. You can see the pressure is held constant through all three scenarios. But what's happening here is that they're increasing and decreasing the temperature. Did you notice this, that the tails on the gas molecules or gas atoms, whatever they are, the tails get smaller? Here you have a tail, and then it gets a little smaller when you go to a lower temperature. So again, as the volume goes down, as the temperature goes down, the volume decreases, and as we crank up the heat, right, the particles of gas start moving faster, and so they take up more space. Anyhow, Gay-Lussac's law, I've kind of been avoiding that, but Gay-Lussac's law says that pressure is also directly proportional to temperature. And so as you crank up the temperature on a gas, it increases the pressure if you hold the volume constant, and as you lower the temperature, the pressure decreases. So we can write Gay-Lussac's law as P1 over T1 is equal to P2 over T2. And you have to have Gay-Lussac's law memorized as well. Anyhow, something else I wanted to point out before I move on to the next slide deals with the tails. Okay, as you crank up the temperature, right? As temperature increases and the tails get bigger and bigger, what does that mean? That means the gas particles are moving faster and faster. And since pressure was defined as force per unit area, since the molecules are moving faster, or atoms, whatever they are, the particles are moving faster, they're going to collide with the walls of the container with a greater force. Okay, so that is why the pressure increases. Anyhow, all kinds of stuff we could talk about here. I could probably talk about this for another 20 minutes, but I'll spare you that. And we'll do a problem. It deals with Charles' law. Did I even solve this problem? Good gravy. Well, I don't think I did. Let's give it a shot here. It says 2.5 liter sample of gas at 25 degrees Celsius is heated to 50 degrees Celsius at constant pressure. Will the volume double? Hey, that's a good question. All right, Charles' Law, V1 over T1 is equal to V2 over T2. Hey, look at this. Temperature doubling, all right? Going from 25 degrees Celsius to 50 degrees Celsius. Will my volume, will it double? Can anybody answer that? Just yes or no. Is my volume going to double if my temperature doubles? Jamil, you're very sharp, okay? I've asked this question to many students, and they'll say, yeah, temperature's doubling. Volume's going to double, man. Jamil, why did you say no? You've got to have a good reason, because I just said temperature double. And it could be a one-word answer if you want. It could be a very short answer. So he says, no, the temperature is not going to double, okay? The answer is no, it will not, because T must be in Kelvin. Charles' Law does not work unless temperatures are reported in Kelvin. So let's solve part 2. We've got our V1, which is equal to 2.5 liters. We've got our T1, which is 25 plus 273, so that's 298 Kelvin. And then we have our T2, okay, which is 50 plus 273, so 273 plus 50, which is 323 Kelvin. Now we can rearrange our formula. V1 over T1 is equal to V2 over T2. We're going to solve for V2, which is going to be equal to V1 times T2 over T1. Now we can plug in some numbers. V2 is going to be equal to 2.5 liters multiplied by 323 Kelvin divided by T1, which is 298 Kelvin. Look at this. Temperature units cancel, and we're left over with our V2, which is 2.5 times divided by 323, and it's going to be 2. Did I do that right? 2.5 times 323 divided by, oh, I put them in wrong. It's 2.71. So we end up with a volume of 2.71 liters as our final volume. All right. The next question asks us, what temperature would be required if we wanted to double the volume? This is just another application of Charles' Law. I'm going to erase some of this stuff here just to create some space while I'm doing this. You guys can give this one a try. The old college try, do it for Clyde. Beautiful mountain lion. There we go. Okay, let's try number 3. If I want to double the volume, my initial volume is 2.5 liters. What's 2 times 2.5? I want my V2 to be 5.0 liters. All right, my T1 is equal to 298 Kelvin, and I want to figure out what is my T2. All right, I can rearrange this formula here and solve for T2. T2 is going to be equal to V2 times T1 divided by V1. We'll put in some numbers. In fact, maybe I should move this out of the way so I have more space. So we'll write down here, T2 is equal to like that. Units of volume cancel. And we're left over with our T2, which is 5 times 298 divided by 2.5. And we would have to crank that up to 596 Kelvin. 596 Kelvin, and that is equal to 323 degrees Celsius. So we'd have to raise the temperature by a hell of a lot in order to get the volume to double. Okay, so T2 is 596 or 323 degrees Celsius. Give me a thumbs up if you follow me on that problem. I could do that. Anybody? Any of my students out there? All right, thank you, Violet, Liv, Aaron. Excellent. Perfecto. Right. Well, let's see here. Da-da-da. Thanks, Brianna. Excellent. Good. Okay, well, let's move on. Who's enjoying gases so far? Kind of fun. All right. Well, now we're going to put Charles and Boyles Law together in what we call the combined gas law. Because if a sample of a gas undergoes change in volume, involving volume, pressure, and temperature, N is constant, write that over here. Number of moles is constant, the amount of gas. We can combine those laws together to get the combined gas law. So look, if you block out, and I know you can see, if you block out the temperature, what do you have? You have Boyles Law. If you block out what? If you block out pressure, then you have Charles' law. If you block out volume, then you've got Gay-Lussac's law. Okay. Anyhow, but you can just say it's combining. You're really just combining Boyles' law and Charles' law to get the combined gas law. P1 times V1 over T1 is equal to P2 times V2 over T2. All right, let's look at one more law. This will be our last law for today, I think. No, let's try practice problem. Keepers. I put in all these practice problems and I didn't solve any of them. Normally, your teacher solves his problems before coming to class. Anyhow, combined gas law practice. Let's write down the combined gas law, which is P1 times V1 over T1 is equal to P2 times V2 over T2. Okay, calculate the temperature when 0.50 liters of a gas at 1 atmosphere and 25 degrees Celsius is compressed to 0.50 liters of gas at 5 atmospheres. Okay, so we're looking for T2 is what we're going to end up solving for. And we can rearrange our formula as being T2 is equal to P2 times V2 times T1 divided by P1 times V1. What are the variables that we've been given? We know that our initial volume, our V1, is equal to 0.50 liters. Our P1 is 1.0 atmospheres, and our T1 is 25 degrees Celsius, which is equal to 298 Kelvin. We know that the final pressure, or the P2, is 5.0 atms, and we know that the final volume, or the V2, is equal to 0.50 liters. So now it's just a matter of plugging all of this into our equation. T2 is equal to P2, which is 5.0 atmospheres, times our final volume, 0.050 liters, times our T1, which is 298 Kelvin, divided by P1, which is 1.0 atmospheres, multiplied by V1, which is 0.50 liters. Before we start punching things into our calculator, why don't we be 100% sure that our units work out? Because we get a lot of them here. Atmospheres cancel, as do liters, and looky, we're left over with the beautiful Kelvin, so that seems to make sense. Now we'll solve this for our temperature. We have 5 times 0.05 times 298. We're going to divide all that by 0.5. Sorry, I messed up. 5 times 298 divided by 0.5, and we get our T2 is being 149 Kelvin. And so, all right, there we go. A little practice with the combined gas law. Remember, combined gas law is P1 times V1 over T1 is equal to P2 times V2 over T2, like that. And remember that N is constant. the number of moles is constant when we use the combined gas law. All right, here we go. This is the last law that we're going to look at today, and it is called Avogadros Law. It was developed by the same Avogadro who came up with Avogadros number. And Avogadros Law states that volume is proportional to the number of moles. Written another way, it says here that volume is equal to a constant, K, times number of moles. And so if we use the initial and final method, and we assume constant temperature and constant pressure, we can write Avogadros law as initial volume over initial number of moles is equal to final volume over final number of moles. And so this is one case where you can use a balanced equation. You can actually use the stoichiometric coefficients in a balanced equation to relate the number or the volume of gases. So if we combine 3 moles of hydrogen gas, let's say, with 1 mole of nitrogen gas, we end up producing 2 moles of ammonia gas. But you see here that for the 3 moles of hydrogen, it takes up 3 volumes. For the 1 mole of nitrogen gas, it takes up 1 volume. So you're adding up a total of 4 volumes of these 2 gases together, and you only end up with 2 volumes of gas. So again, volume of the gas is directly proportional to the number of moles, Avogadros law. And again, this is one case where we can use the stoichiometric coefficients found in a balanced equation to help us express the volume of a gas. Here's another figure that represents Avogadros law. And you see here that you have a certain amount of volume associated with these 1, 2, 3, 4, 5. There's 5 particles of gas here. And what happens as we increase, no, they haven't written here, but we increase the number of particles, what happens? Right, we're at constant pressure, okay? But as we increase the number of particles, what's going to happen is it's going to take up more space because volume is proportional to number of moles. Written another way, like this. So as volume goes up, number of moles is going to go up, right? Here, the same thing. We're adding gas molecules. So what's going to happen? The volume is going to increase. Nothing more than that. Remember, this is at constant temperature and pressure. All right, well, let's move ahead. And we're not talking about a new law here, but I want to introduce a new equation in a few minutes. And before we do that, we're going to look at a practice problem that deals with Avogadros law. Again, Avogadros law is V1 over N1 is equal to V2 over N2 at constant P and T. If we have 5.50 moles of carbon monoxide and it occupies 20.6 liters, how many liters will 16.5 moles of carbon monoxide occupy at the same temperature and pressure? Let's start by writing down our formula. V1 over N1 is equal to V2 over N2. What are we given? We're starting with this many moles. That's going to be equal to our N1. That's the number of moles we're starting with, 5.50 moles. And I'm going to skip right ahead to how many moles we're ending up with. So we're ending up with N is equal to 2 of 16.5. So we're increasing the number of moles of gas. The initial volume, where we started out with, our V1 was equal to 20.6 liters. And we're solving for what's the final volume, V2. Can anybody tell me, does anybody have a kind of an intuition here as to whether the volume is going to increase or decrease?
You never know what to expect from
Ashlyn says increase. Let's check. Let's solve for V2. So if we rearrange this equation for V2, we get V2 is equal to V1 times N2 over N1. Let's plug in some numbers. We have 20.6 liters multiplied by our initial number of, our final number of moles, 16.5. Then we're going to divide that by our initial number, which is 5.50 moles. Look at this. Number of moles cancel, and we end up with a V2, which is 20.6 times 16.5 divided by 5.5. And we end up with 61.8 liters. There you have it, folks. Ashlyn was 100% correct. She said, based off of Avogadros Law, if I'm introducing more particles, right, she knew that N was increasing, so V was going to increase. All right, there we have it, folks. Avogadros Law. You saw it here first. Well, maybe some of you did, but maybe some didn't. Okay, if we look at Boyles Law, Charles' Law, and Avogadros Law, we see that from Boyles' Law, volume is inversely proportional to pressure, right? You see the formula that's written here. I can also express that as V is equal to K divided by P. So volume is inversely proportional to pressure, okay. From Charles' Law, we see that volume is directly proportional to temperature, and that from Avogadros' Law, volume is directly proportional to number of moles. We can express all of those V's, right, as volume is going to be proportional to N times T divided by P. Now that's proportional, right? This symbol here means proportional, proportionality. Okay. Another way we can express that is to say that volume is going to be equal to a constant multiplied by NT over P. And that constant is called R, big R, and we call that the gas constant. Now, the most commonly expressed form of this equation is not V is equal to RNT over P. It's usually written like this, okay? PV is equal to nRT. Sometimes I hear people call this Pufnert. I don't know. I don't ever say that, but my students do from time to time. That's cool. That's cool. Now, this equation will never be provided to you. You have to have what's called the ideal gas equation. So this is the ideal gas equation. You have to have this memorized. Memorize. Okay? Now, you might notice something interesting about this formula. And, you know, about a lot of the formulas that we looked at today. There's nothing in here, pressure, volume, number of moles, temperature. There's nothing in here that's related to the nature of the gas, right? Is this equation for chlorine gas, for helium gas, for argon gas, to carbon dioxide? It's not for any of them. It's for all of them, because there's going to be no differences between gases when they are considered as ideal gases. Let's talk about something called standard molar volume. And we're going to need standard molar volume in order for us to calculate what R is. If we go back to that equation, PV is equal to nRT. Remember that this equation is good for any gas, any ideal gas. Doesn't matter. Sulfur dioxide, chlorine, helium, argon, I don't care. Okay, so that means that my R is going to be equal to PV divided by NT. Now, in order for us to solve this, if we had 1 mole of a gas at standard temperature and pressure, what volume would that gas take up? Let me show you. It doesn't matter if you have 1 mole of helium gas, 1 mole of nitrogen gas, 1 mole of oxygen gas. 1 mole of any ideal gas that is at standard pressure, 1 atmosphere, standard temperature, 0 degrees Kelvin, or sorry, 0 degrees Celsius rather, not 0 Kelvin. No. The volume is always going to be the same. Okay? And you need to have this volume memorized. Okay? At standard temperature and pressure, the volume of 1 mole of any ideal gas is going to be equal to 22.4 liters. Always going to be equal to that. Okay? So if we have 1 mole of a gas, right, at standard temperature, 273 Kelvin, standard pressure, 1 atmosphere, and we know that this volume is equal to 22.4 liters, we can plug those numbers in and solve for the gas constant. The conditions of 0 degrees Celsius or 273 Kelvin and 1 atmosphere are called STP, standard temperature and pressure. And as I told you, experiments show that at standard temperature and pressure, or STP, 1 mole of any ideal gas takes up 22.4 liters. Now, if you Google this, you'll probably see that it actually takes up 22.414 liters. If you need more than 3 sig figs, then go ahead and you could use all of those. But look, if we have a gas at 1 atmosphere and we have 1 mole of it at standard temperature, we know it takes up 22.4 liters. If we divide 22.4 by 273 and put in all our units, we see that R, or the gas constant, is equal to 0.082057 liter atmospheres per mole Kelvin. I usually write it like this, 0.08206, because usually we don't need more than 4 sig figs liter atmospheres per mole K. That's how I will write it probably 99% of the time. Other textbooks will just round it off to 3 sig figs. They'll say 0.0821. That's fine too. And it all depends, again, on how many significant figures you need based off of the problem that you're working on.